तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Phi, a variable scalar field was given, and that the observer was supposed to move with a velocity v. We said it's equivalent to calculating material derivative. It's a relative term. Whether observer moves or the material particle moves, it's all the same. So what you do is to calculate dou phi by dou t, then calculate dou phi by dou x, or in other words grad of phi, then calculate phi dot by first term being dou phi by dou t as grad of phi dot v. So the answer happens to be x into 1 plus so that's the material time derivative of phi. Now let's move to the next problem. Next problem is the same way we will do it. Prove that E dot is equal to D minus L transpose E minus EL. So I'll give you a couple of minutes. Let's see how you work out this problem. Remember what was our E? E is the Eulerian. Note that it is the Eulerian strain rate, or strain rate which is strain which is referred, or Almansi strain, that is, in other words, is referred to the current coordinate system, and it was written as half into I minus F inverse transpose F inverse. So I am interested to determine what E dot is. Let's see. Continue with that. Obviously the first term will not be there, so this will be half of F transpose T F, the whole is to be differentiated with respect to time. How do you write that? What is the relationship between L and F dot? L is equal to F dot F inverse. Keep that in mind. So substitute that and see what you get. So what will happen to the first term? Okay, do that, and you will ultimately get L transpose into I minus 2E plus I minus 2E L note that D is half of L transpose plus L. So from this you can write this down as D minus L transpose E minus EL. Okay, fill up the remaining steps. We will move to the next problem, just substitution and then just working it backwards. Okay. Now, both the problems are very simple problems, only thing is that you have to manipulate a bit. Okay. Well, let us go over to the next problem. Consider a deformation gradient, that is f, given by what I am going to write now. Consider the deformation gradient f given by C minus AS, AC minus S, S plus AC, AS plus C. Of course, C is equal to cos theta and S is equal to sin theta. Take for this problem A is equal to half and theta is equal to pi by 2. Find the, this is the third problem, find the stretch tensor, find the stretch tensor, or in other words, sometimes U is called a stretch tensor, U and R. U, which represents the pure stretch, is called stretch tensor. Find U and R. So, in other words, substituting these things, you can first write down what is F. What is F? Cos pi by 2 minus, so minus half, first term. The second term is A cos theta, again that goes to 0. So, minus 1, right, and then 1, again C goes to 0 and half. So, the first step is to find out C. Okay, look at these steps, what I am going to do. C. C is F transpose F, okay, determine F transpose F. So, the steps we are going to follow is that we will find out C, solve the eigenvalue problem, determine the eigenvalues of this and as well as the eigenvectors, okay, write the eigenvalues of U. Okay, what is the eigenvalue of U? What is the relationship between that and eigenvalue of C transpose C? Root of the values, and then determine the eigenvectors, transform U to the original coordinates, okay, and then determine R, because you know F and you know U. So, now determine F transpose F. If you have forgotten something, please refer to your notes and tell me what is F transpose F. 5 by 4, 1, 1 and 5 by 4. So, the next step is to find out lambdas for C. Please determine lambda, write down, is very simple, straightforward, because it's just 2 by 2. Write down the characteristic equation and then find out what lambda is. As well as for the lambdas, determine the eigenvectors as well. Determine the eigenvectors as well. Very good. So, lambda 1 is equal to 0.25 and lambda 2 is equal to 2.25. Find out the corresponding eigenvectors for lambda 1 and lambda 2. This lambda 1, lambda 2 are the eigenvalues for the C. We will take the square root for u. But meanwhile, let me determine the eigenvectors for these two quantities. That is, in other words, V of 1 and V of 2 corresponding to the eigenvalues lambda 1 and lambda 2. 1 by, you have to normalize it, 1 by root 2 correct, 1 minus 1, 1 by root 2, 1, 1. Very good, that's excellent. So look at these steps, this is how you calculate stretches and as well as, because these steps or these kind of calculations may become very important when you do finite element analysis, when you implement finite element analysis later. So in other words, how do I write the C matrix? So C matrix is in terms of, this is spectral decomposition, in terms of these lambdas are written as 0.25 or 1 by 4 if you want, you can write it as 1 by 4 and as someone said 9 by 4, right? And the corresponding, what do I mean by basis for, in this case? In spectral decomposition, remember that we had written for spectral decomposition lambda 1 V1 V1 plus lambda 2 V2 V2. So the basis here are the eigenvectors, correct? So those are the these are the bases. So in essentially, what is that we have done? Just to recapitulate what we know. Essentially, what we have done is to get a basis, new basis, in such a fashion that we get diagonal C matrix. This is exactly what you do in, say, for example, when you do vibration problems. You find out the eigenvalues and eigenvectors, and then change over the basis. Your original basis is now replaced by the eigenvectors. What exactly you do? You decouple all those equations. The governing differential equations, you decouple them. So basically, eigenvectors are used to change the basis, okay, so that it becomes the matrix, ensuing matrix. In other words, the ensuing equations in the other case, free vibration problems or vibration problems rather, would be much easier to solve. Okay. Now, how do I determine u in this basis? So that's simple. Square root of these guys here, 2, 0, 0, 3 by 2, right? But my job is not yet over. What is that I should do now? What is that I should do? Now this is in this, what we have got here is in this basis. Now I have to get it back to my original basis. So how do I do that? Look at this and see. You have to do a transformation. Please look at that. Let's see how much you remember from what we did earlier, and then write it down. So in other words, the basis actually can be written as 1 by root 2, 1 minus 1, 1 and 1. So this multiplied by u multiplied by transpose of this would give me the u value in the That is the transformation that I am going to use. Okay, u or the value of u in my old coordinate system. Okay. So, let us see how we do that. So, in other words, 1 by root 2 1 minus 1 1 1 half cipher 3 by 2 into, write it here, 1 by root 2 1 1 minus 1 1 would be the transformation matrix. So, what is the result of that? 1 by 2, 1 by 2. So, you can take it as half so the answer is, if I am correct, 2 by 3 2 minus 1 minus 1 2. Just check this up, see whether you get this. Just check that. So, essentially the steps are very clear, right. Just find out the eigenvalue, go to the spectral decomposition mode, it is a standard step, determine the eigenvalues. Okay. So, this is a very practical way of decomposing f into the stretch term u and the rotation term r. So, I hope this is correct, right. Please check this up. No, I just did that fast, I hope it is okay. Now, how do you determine r? Yes, that is all. So, invert it, fu inverse, calculate fu inverse and calculate r. Please invert that and find out what r is. R is equal to fu inverse, f you already know, invert u to get u inverse and then please attempt the problems, all the problems as we go along, please attempt it. I think this is u inverse actually. Sorry, this is u inverse. U inverse is this, and u is actually half of u is half of 2 1 1 2, because 1 by root 2 1 by root 2 is half of it, then you multiply this 2 1 1 2. This is u. And actually this is u inverse, they had already inverted it. So, that is u inverse into 2 by 3, obviously we will not get 2 by 3 here because 1 by root 2 1 by root 2 is here, so we will get only half. So, u inverse is equal to 2 by 3 2 minus 1 minus 1 2. So, 2 minus 1 minus 1 2. So, r is equal to 0 minus 1 1 0. Note that this is u inverse, not u. This u is here, just you have to multiply those terms there. 1 by root 2 1 by root 2 goes out to half. So, other multiplication gives you this, inverse of that is given by take the determinant, okay, then cofactors, write down the cofactors, just 2 by 2 matrix. So R gives the, you can easily note that R transpose is equal to I, okay, which is our result. Right, any questions on this problem? Now take down the next problem. The uniaxial, we are talking now going to talk about uniaxial stress and the associated strain, okay. How this condition can be expressed in terms of the first Piola-Kirchhoff stress, the second Piola-Kirchhoff stress, and of course the Cauchy stress, and what are the strains. Different strains are capital E, small e, and so on. So consider a bar okay, with length L, B and A. Let us say that its original dimensions are L0, B0 and A0, and its final dimensions are, say, given by A, B and L. Let us say that a uniaxial stress state is what is applied to this bar, right. So determine the nominal stress second pk first for this bar. Right, take the directions to be, say, this is the x direction or capital X or capital X1 if you want to write it as capital X1, and then that to be capital X2, or in other words X2 is in the, or you can X2 and X3 to be careful, and yeah, that's X3. The right handed coordinate system should be maintained, and so X1, X2 and X3. So our first job here, what is that we should do? Of course sigma you know. So the Cauchy stress is nothing but, say, sigma 1 1 or sigma x 0 0 0 0 0 0 0 0. That's fine. But in order that we convert this into the first Piola-Kirchhoff stress and second Piola-Kirchhoff stress, what is that we need? The first thing, F. Very good. So we need F. Now I'll give you 2 minutes. Let's see how many of you come up with what is F for this. No, yeah, it's not L minus L naught. Please first, so your first step should be to write down, say, what is small x1 coordinate. So small x1, okay, in terms of capital X1. And then small y1 and small z1. How do you write this down? Choose a, I mean, I've just given x1, x2, x3. Choose an origin and try to write down x1, y1 and z2. Yes. So first x1, write down. So L by L naught, same what you said, L by L naught into, say, x1, not x1, y1, y1, say x2, x2 is A. So A by A naught into capital X2 and x3 is equal to b by b naught into x3. Very simple. When x3 is equal to b, capital X3 is equal to b naught. Okay, so in other words, this is some sort of an, what is that we have followed here? Linear interpolation between one end to the other end. Okay, that is all. So now write down f. Now you cross the major thing. So now write down f. That is straightforward. Dou x1 by dou capital X1, that is L by L naught. There are no other terms there. So all these terms become 0, 0, a by a naught, 0, 0, 0, b by b naught. Right? Okay. Now what is the determinant or j, determinant of f or j? What is it? Yes. So it's very simple. You know dv by d capital V, dv, d small v is abc. You need not even go through this. Okay, so we'll say abl, rather abl by a0, b0, l0. That is the determinant of j. Now we have to calculate f inverse. So diagonal matrix. So f inverse L0 by L 0 0 0 0 0 0. Very good. So knowing sigma, knowing j, what is that I want to calculate? P, yes, nominal. What is the formula? J, no, that is for from P. So J F inverse sigma yeah, okay, J sigma F inverse transpose, calculate that. So actually we had sigma is equal to Jp F transpose, right? J inverse P F transpose, right? So this will become J sigma is equal to P F transpose. So J sigma F inverse transpose equal to P. Pardon? What is sigma? Sigma is sigma. What is that you get for P? AB, okay, let me write it here. So P is equal to AB by A naught B naught sigma 1 1, rest of it are 0. Right? Look at this, what this indicates. AB into sigma 1 1. AB is what? The current area. So Cauchy stress is for the current area. So that area multiplied by sigma 1 1, what do you get? The force that is acting. Okay, that divided by the original area. That is why this is called as a nominal stress. So, obviously, I mean you could have guessed it, but nevertheless it is very important that you go through the whole steps, because that will give you the whole thing. So, this is the force divided by the original area would give you P. Now, calculate yes, the second PLO Kirchhoff stress. Second PLO Kirchhoff stress, we already saw that it is the pullback that we have to apply on the Cauchy stress. So, rework that here. So, what is the relationship between sigma and yes? F inverse sigma F transpose is equal to yes. Sigma transpose is equal to sigma anyway, it is the same. So, let us take the S11 term, just work it out and tell me what is the first term, the S11 term. Yeah, AB sigma 11 by A naught B naught into L naught by L. So, everyone get this answer? Into L naught by L. Yes, I think that is right. So, look at that. Here in for P, we were able to give a physical meaning for P, but for second PLO Kirchhoff stress, we are not in a position to give any physical meaning for it. It is just a pullback operation, and that is how you should view it. You should not look at PLO Kirchhoff stress as something which we can physically relate to. Yeah, this poses problems. This poses problems especially when you give results, and when you go to plasticity, when you deal with second PLO Kirchhoff stress, since it does not have a physical meaning, and many of the quantities that we deal with ultimately, especially when with respect to yielding or failure and so on, they have a physical meaning. So, when you deal with this PLO Kirchhoff stress, second PLO Kirchhoff stress, you have a problem, agreed that. So, we will overcome that by different things, and in fact, you would notice that none of the softwares give results in terms of second PK, though internally many of them work with second PK, they will not give you results on second PK, basically because it does not have the physical meaning. But that should not worry you when we apply these things, because you should view it as a mathematical operation of pullback. So, that is the reason why you will not, apart from theory, you will not see these things in results. The results are still given in terms of the Cauchy stress. All the results that are still given in most of the softwares are in terms of the Cauchy stress. Yeah, first PLO Kirchhoff stress, right. So, you can develop a relationship between P and S. I leave it to you, it is very straightforward to develop. Please develop a relationship between P and S. But keep this in mind, and we will encounter second PLO Kirchhoff stress quite often in the implementation levels. But if you just use it, you will not encounter second PK or second PLO Kirchhoff stress. But there is today a tendency, especially in biomechanics, to actually plot graphs in terms of second PK itself. Though there are, I am not sure whether how much that is the correct way to approach things, because this does not have a physical meaning, but still what people do is to calculate sigma, calculate F, and plot the graph second pk versus E. Okay, there's been recent literatures which show experimentalist plotting second Piola-Kirchhoff stress. But personally, I feel that that doesn't take you anywhere because you do not get a physical picture of it. Okay. So let's look at the next problem. I'll just give that problem to you. This will be our fourth problem. The deformation of a body is described, the deformation of a body is described by x1 is equal to minus 6 x2, x2 is equal to half of x1 and x3 is equal to 1 by 3 capital X3. If sigma is given by 0, 0, 0, 0, 50, 0, 0, 0, 0, sigma is given by this, determine Cauchy stress vector T, Cauchy stress vector T and the first Piola-Kirchhoff stress vector. Note the difference between stress tensor and stress vector. We have emphasized that in our first course. We know that stress can be looked at as a vector and as a tensor. So sigma n or sigma transpose n is equal to a vector, that's a tensor. Okay. And calculate the first pk stress vector taking n to be E2, taking n to be E2, the unit vector along the second direction, and then calculate what is the stress vector and for both Cauchy stress and the Piola-Kirchhoff stress. So our first job of course is to calculate from this F of course what do you get here? P. What do you get here? Same P n. Note the difference between small n and capital N. Small n is the normal at the point of interest, okay, along a surface ds in the current coordinates, and capital N is the same normal in the reference configuration, the reference coordinate. Okay. So note the difference between the two. So your first job now is to find out F. Dou x1 by dou capital X1 is 0, minus 6, 0, half, 0, 0, 0, 0, 1 by 3. So I need F inverse transpose, right? So calculate F inverse. Calculate F inverse. Zero, 2, 0, minus 1 by 6, minus 1 by 6, 0, 0, 0, 0, 3. That is F inverse. Yeah, F inverse transpose. Oh, this is F inverse transpose. Yeah, F inverse, that's F inverse. So you have to calculate F inverse transpose and then calculate P. Of course, determinant J I think happens to be 1. Calculate the determinant of F, that is determinant of F, that's equal to J is equal to 1. So calculate P now. P happens to be 0, 100, 0, 0, 0, 0. Okay. Now I have to calculate capital N, the normal. How do I calculate it? Nansen's formula. Okay, right. Just calculate what is capital N. So N ds is equal to J inverse F transpose N ds. So what happens to this? Half E1, yeah, ds. Check that up. Is that right? Yes, very good. So half E1 ds. So what is N? N is actually the, yeah, so what is N? So it is the unit vector along E1 which is equal to E1 itself. So obviously, so ds is half of ds, that is it, because this is a unit vector, E1 is a unit vector. Okay. So I can rearrange this as E1 half ds. So that is the magnitude, this is a unit vector, this is a unit vector, this is a magnitude. So ds is equal to half ds, right? That is straightforward. So look at that, N which was E1 has become now small n which is E2. Yes, so find out the traction or the stress vector sigma n. Very good. So that happens to be 0, 50, 0. Now what happens to P? Yeah, 0, 100, 0, very good, 0, 100, 0. Obviously you need not even calculate that because I see that I told you already, I gave the clue that ds equal to half ds, so obviously that is 100, 0. Okay. So that completes a few problems that we were able to do. Okay. So you now know how application is done, which is very straightforward. Okay, if there are any questions. Okay. So with that we will close the topic on stress. So we will move over to a few more fundamentals that we have to learn before we get back to the nonlinear finite element analysis.
How the software knows these functions?
Yes, the softwares have these things, okay, as routines, calculation of U, calculation of R, and so on. We will see more about that when we come to the formulations of elements in terms of these quantities later.
Is there anything like shape function for P quantity?
Yes, of course, there are shape functions that are defined. We will see about them during the formulation. Okay, we will close now. See you.